Okay, we can start. If you have any question, you can ask me. You can input your question from the chat, through the chat. Uh, about the grading, let me check. I think the weight of the grading for each project, each homework, and the examination, each examination is correct. We don't have the final term yet. We don't have the project 2 yet. Yes, I believe the examinations have a larger weight. Yes, the weight is correct. Okay, about cash. Now I'm sharing my slides. I believe the cash part is good question. So this is the so-called direct mapped cache. So since you have reviewed some questions in the final review slides, you know that we have so-called block. Block is the size of each cache line. For example, if you have a 32 bytes, let me think. No, 64 bytes. 64 bytes block. So this is a 2 to 6, which means that we need 6 bits to index these many bits or these many bytes inside that block. That's the reason why the block offset is 6 bits from 0 to 5. 0, 1, 2, 3, 4, 5, 6 bits, okay? And we have an index here. The index is the index, of course, it's the index for the blocks, for the cache line. Here we have 15 minus 6 plus 1, which is 10 bits. For 10 bits, we can index 2 to 10, which is a 1K cache line here. So I have 1K cache line. Each cache line is 64 bytes, which means that the total size of this cache is 64 kilobytes. So the total size here is 64 kilobytes. So this is how we can calculate the size, the address, the index of the direct mapped cache. First, you need to understand the block offset. If each cache line is 64 bytes, then you have 6 bits here. How about if it's each cache line is 16 bytes, then you only have 4 bits. And then you can use this total capacity divided by this block size. Block size, yes, it's a block size, not a block offset. Each block size is a 64 bytes. So then you have a 1K line, 1K index if it's organized as a direct mapped cache. So for 1K index, you need 10 bits from bit 6 to bit 15. And because maybe your address is 64 bits in this case, so all the other bits address should be tagged. So if it's 32 bits, then this is a 31. So all the other bits except the index and the block offset are all tags for direct mapped cache. And for the direct mapped cache, how can we, look up the cache? How can we access this cache? Yes, this is a very good question. Why we select the index bits here? As you know that the memory is organized as a consecutive blocks. You can view the memory like this, like one line, like a SRAM array. So here is one block, the second block, the first block, the second block. This is the first block, the second block. And each block is 64 bytes. Which means that the address of the first block is what? Is a 0 from 0. It's a from 0 to 33, okay? And then the starting byte of the second one is 64 bytes to 127 bytes. So you can see that if I translate the address here to 64 bytes, the first block is from, I have 64 zeros here, from all 0 address to 64 is 226, yes. So I have 1 0 0 0 0 0. Yes, this is 6 bits, and the first bit is 1. So in the binary, this indicates the 64. So I have this 64 from all 0 to this 64. You can see that what changed? Only this 6 bits changed, right? From all 0 address to this 64. This is the reason why we use, these 6 bits to serve as the block offsize, because you consecutively store the data. Your first block is from all 0 address to, I'm sorry, this is a 30. This is a 30. I'm sorry. This is a 63 bytes. It's from all 0 to 63 bytes. So this is a 0. All here are 1. This is a 63. So your first block is actually from all 0 to we have 5 ones here from this address. Based on these address pattern, we can see that only the last 6 bits actually changed. So this is a reason why we select the block offsize as the last several bits, because they consecutively stored. Why we use these bits as the index? This is the second part of the question. Why? Because potentially our application have a so-called spatial locality, which means that if I access the first block here, very likely I will access this block. So I prefer what? I prefer to store these 2 lines simultaneously in this cache, right? In this cache. So that's the reason why I selected these as the index, because each line here is related to one index. This is the second part. How can we look up this one? We do the lookup by doing a mode operation. For example, we use this index. We use your address. The address except this block offset. I use this address, this part of the address, do a mode operation. Mode what? Mode how many physical line do you have? Now you have 1K. So I use the address, use actually the partial address to mode 1K. So that's the reason why this line will be stored in the first block. The second one will be stored in the second block. Why? Because this address, if I use this address, these parts of the address, which are all 0, to mode 1K, the result is, of course, all zeros. So I store it in the first which is a block 0 in the cache. As I said, the address of this guy is all 0, and I have a 1 here and 5 zeros. Because this binary indicated the 64 bytes, so the starting address of the second line is of course the 64. So I use all these parts to do the mode. The result is 1, so I store the data here in the second block. So only I use these bits to serve as the index. I can simultaneously keep these 2 lines in the cache, so that next time when I access these lines, I can have them both in cache. If you use these tag bits, for example, the first 10 bits as the index, what will happen? For the first block, these bits, of course, are all zeros. Then this bit is mapped to the first data line. For the second block, this bit, if I want to access, then I do the lookup. I found that the address of this guy, the first 10 bits here are also zeros, are all zeros too. Then this guy are also will be mapped into the first. So these 2 guys will compete for the first line. So this is not good because I have a spatial locality. I want them to be mapped into different, cache lines here. That's the reason I use the index in the Mino. I use the bits in the Mino to serve as the index. Otherwise, if I select here, you know that this is the first one, this is the second one. For all the first several blocks, these 10 bits are all zeros. So all zeros bits will be mapped into the first physical lines here. This is not good. They will compete for the first blocks. So in this case, I cannot simultaneously hold them into the cache. Then if I have very strong spatial locality, this is not good. The question is, can we program the hardware to read the index as a group of bytes from the most significant? Yes, you can program. You can configure, so-called configure your hardware to do that. But as I explained, it's not good to read to use the most significant bit as the index. Why? Because for the first several blocks, they will compete for the first line here. For the first line, these bits will these blocks will compete for the first line here. Only one of them can be stored in the first line, and this is not good if you have a strong spatial locality. Any question about the direct mapped cache? Direct mapped cache is the so for example, this is your this is your third block. When you try to find the third block in this cache, you just fetch its index and then go to the corresponding block in the cache. For the third block here, the corresponding one is of course the third one. You compare the tag. If they are the same, you get a hit. Yes, the exam will be performed in the same format as the last time, as the midterm. Yes, we will start from 9:25 a.m. To 10:40 a.m. Yes, that's right. I'm just talking. I will record the question too, but I will explain the set associative cache and fully associated cache. So the fully associated cache means for one line, for this line, you can store any blocks here. You can store this guy to any of them. But in a direct mapped cache, you only have one option, which decided by the index. Your index is 3, then you go to the third one. But if it's a fully associated cache, then you can go to any blocks here. That's the reason why during the lookup you need to compare against all the blocks, the lines here, to decide which line exactly you store your data in. So you have the maximum flexibility here, and you have the so-called minimum flexibility here, because here you have all the options. If you have 8 blocks here, you have 8 choices. Here, if you have 8 blocks, you only have one choice, one only option. This is your only option. The set associativity is some combination. First, they, although you have 8 blocks, they group it into 4 large groups. Your first step is to decide you can only choose one group, large group. For example, you select this group. Within this group, you can store your data in any blocks here. Because in this group, you have 2 blocks, then you have 2 options. So the set associativity is somehow is a combination between the fully associated cache and direct mapped cache. And you can achieve, both. You can have multiple options, but not all the options. You can have some options if you use the set associativity. Then I will go to the second question of the review. About the review about the second question. So the second question is about the destination register and the data. What's this? So what's the function of these two? Assume that you want to calculate this equation. Assume you want to calculate this arithmetic operation. So the register A is this guy. Register B is this guy. You decode them and you get the value of A and B. You go to the next stage, which is the execution stage. You get the result here by the ALU, by a function unit. Then in the write back, in the final stage, which is the write back, you need to write the value of C to the register C. The register C is a register fabricated along with the register A and B. So all the registers are in the same register files. We have A, B, C here. When you do the decoding, you read the value of A, you read the value of B. When you do the write back, you write the data. For example, I do a 5 plus 5, which is a 10 here. I put a 10. 10 is the data. Destination register is the C. Then I write this value to the C register here. So this is very simple. Any question? So this question is about the write back. You just write the value back to the register C. And here I also give you another operation, which is a load. You load for example, if an instruction is a load some data, the data from the address of 100 to C. You do the decoding to know, okay, the address of this 100, and then you visit the memory, you get the data back. For example, the data stored here is 16. And you want to store this 16 to the register C. So the destination register here, I'm sorry, let's change a register. Let's call it a E. The destination register here is a E, and the value here is a 16. Data is a 16. So they basically, the memory instruction and the arithmetic instruction are similar in this case. Any question? I don't think the time. I think you have enough time. So because most questions are exactly the same as the review. And you can prepare some papers if you don't like to, have the examination on computer. You can write your answer on some paper, and then you give me some pictures, send me some images. I think you cover the final review covered all the topics. No new topic will appear in the final examination. First, it's about a 5-stage pipeline, right? Question. The review of the question. Question 1, question 2 are pipeline. 4 are pipeline. 4 also pipeline. This is pipeline. About cache. Cache is about cache is the Q5, Q6. Q7 is a virtual memory. Q8 is DRAM. Q9 is a combination of DRAM and cache. Q10 is still cache. That's all. Cache, DRAM, 5-stage pipeline. Virtual memory. Virtual memory, I can tell you that virtual memory, if you have some question on virtual memory, then it's the question. It's the question 7. So do not worry about virtual memory. I know that only few of you can understand the virtual memory. So if we have a virtual memory question, then it's question 7. So do not worry about this. Make sure you understand the 5-stage pipeline, DRAM, and cache. Yes, 2 or 3 questions are not from the review. That's right. But they are still on the topic of 5-stage pipeline, DRAM, and cache. Yes, of course, DRAM. DRAM, there are several. So the first point is the open page policy and the closed page policy. Why do we have an open page policy and a closed page policy? This is because we have the destructive read. The destructive read means no matter your DRAM store 1, which means that the capacitor here has some charges, or your DRAM cell store 0, which means your capacitor has nothing. After a read operation, the voltage inside this capacitor is 0.5. Why? For example, if you have, in order to read the cell, we pre-charge the bit line. Here, this is the bit line, into 0.5. So if your voltage here is a 1, 1 means VDD. If you have some charges here, then your charge will flow from the capacitor to the bit line here. So the bit line voltage will go up. This is go up from 0.5 to 0.7 or 6 something. So in this way, the sense amplifier can sense the data out. I noticed that your voltage increased. Then I evaluate you as a 1. But the voltage inside this cell is from a 1, which is a VDD. Change from 1 VDD to 0.0. I'm sorry, 0.5. On the contrary, if you store a 0 here, I still pre-charge the bit line to 0.5. Then some charge will flow from the bit line to the capacitor. So the bit line voltage will go down to maybe 0.1 or 0.2. So your sense amplifier can also notice the changes here. Then I evaluate the sense amplifier will evaluate this cell as a 0. But the voltage inside this capacitor will go up from originally it has no charges, so it's a 0. Then it go up to maybe 0.3 or 5 or 0.3, 0.4, 0.5, something like this. So no matter you store 1 or 0, at the end of the read operation, your voltage are, between 0 and 1. So this is so-called destructive read. If your voltage inside a cell is 0.5 or 0.3, is between 1 and 0, then next time I cannot read you. Then basically the content in the cell are destroyed. We have to do some restore. So this is a cell level read operation. This is the array level read operation. When you do the read operation, you sense the data to the sense amplifier. Now the sense amplifier know whether you are 1 or 0, but the data inside the DRAM cell, in the DRAM cell, are destroyed. So you cannot read the cell again. The real data, the correct data are kept in sense amplifiers. So this is this operation from array level. At the array level is a so-called open array, because this is a row. Then you have two policy. The first policy is that, okay, I just leave everything here. I leave the page open because I hope that next after one read operation, maybe this read operation requests these 2 bits. Maybe next read operation will request these 2 bits. But the read operation will always happen on this page, on this 4K page, let's say 4K page, which means that your application have very strong spatial locality. You want to keep the page open. But if your application is randomly access the whole memory space, which means that next time your application will read another row here, because your array organized like this, you have multiple rows and multiple columns. Each column indicate a bit line. Each horizontal line indicate each row indicate, of course, a page. Maybe next time your application will read this row. Then at that time, you need to restore the data to this row back first, because you open this row. Next time, you need to restore the data, write the data back, and open this row here. So if you feel like you need to, your application has a very small spatial locality, you need to so-called you need to adopt the so-called close page policy, which means that after one read operation, you immediately close this row. You restore the data back to the cell here. Otherwise, if you leave the page open, leave this page open, next time you have another request, go to here and you look up the buffer. Row buffer, you find out you have a miss, you have to write back. That write back is actually on the critical path because you have that pending request at that time. But if you, for the first request, if you, after the read operation of the first request, you immediately close this row, you do the restore. That restore operation is not on the critical path because you don't have any pending request. Otherwise, if you have the second request, you have a pending request, the restore operation will be on the critical path, and this delay will add to your application. So this is the difference between the closed page policy and the open page policy. Any other question? If you have any question, you can email me. The function of this mask is to select between the register B and the immediate data. For example, we have two types of operation, which is A plus B. The second type of this guy is A plus 10. The mask here is used to select this guy and this guy. This guy is a immediate value of data. This guy is a register B. So this mask is used to select between this B and this immediate data. And this ALU in this case is the adder. Any other question? The mask of this guy, the question 4. This mask is used to select between some instruction like so some instruction like this guy, addition, is the result from ALU because ALU do the addition. Some instruction is the memory instruction. The value of this guy, this part, the value of this address is actually read from a memory. And we need a mask to select between the value of these and this one. The sum of this guy, this one and this one. We need a mask to, do the selection. Control bit is just, you have the destination register and write enable. Any other questions? If you still have any other question, you can email me. Please do that. And I think we can stop here today. Thank you very much. Do not worry about examination. The examination, if you carefully review the review slides, I don't think you have any. I don't think you have any question. Any problem in the examination. If you carefully review everything, it should be easy. Thank you very much.